Welcome to another deep dive, and today we're looking at X-ray spectrums,
Oh, cool.
and specifically the factors that influence these spectrums in diagnostic imaging.
Right.
We've got some great material to work with, including some stuff from an X-ray spectrum simulator.
Oh, very cool.
We're going to kind of try to break it all down. So
Yeah.
I think this will be really helpful for anyone who's had an X-ray or maybe even wondered how they actually work.
Absolutely. It's essential knowledge, not just for physicists, but really for everyone. Right. Understanding these factors can help us appreciate the science behind this technology and just how it benefits us.
Mm-hmm. So let's start with the basics. Like, how are X-rays even produced in the first place? I mean, I know they involve electrons and targets, but
Yeah. So there are actually two main ways: Bremsstrahlung and characteristic X-rays.
okay, those are some big words.
They are, but they're not as complicated as they sound.
Okay.
So Bremsstrahlung X-rays are produced when electrons slam into a target material, right? It's basically a collision where the electron suddenly slows down,
Mhm.
and this deceleration causes it to release energy, and some of that energy is emitted as X-rays.
So it's like if you throw a ball at a wall and it loses some of its energy as sound when it hits.
Exactly, that's a great analogy.
So here, the lost energy becomes X-rays.
Precisely.
Okay, that makes sense. And what about those characteristic X-rays?
Right, so characteristic X-rays are a little bit different. Instead of simply slowing down, the incoming electron actually knocks an electron out of an atom in the target. And when an outer shell electron fills that void, it releases energy as an X-ray photon, and this energy is specific to the atom structure, hence the term characteristic.
Oh, that's so cool.
Yeah,
So each element, it has its own unique X-ray signature.
that's right.
Awesome.
Like a fingerprint.
That's really cool. Now, the source material mentions that both Bremsstrahlung and characteristic X-ray production are influenced by the voltage applied to the X-ray tube, or what they call kVp.
Yeah, that's right. Adjusting the kVp is one of the main ways technicians control the types of X-rays being produced. But it also affects the total energy of the X-ray beam, which the source material shows as the area under the spectrum curve.
Oh, okay. So what happens to the total energy when you increase the kVp? Like if the area under the curve represents total energy and you increase the kVp, doesn't that mean you're increasing the area?
Exactly, you got it.
So that means more total energy.
You're absolutely right. A higher voltage means the electrons have more kinetic energy when they hit the target, and that results in a more intense X-ray beam.
Okay, so higher kVp equals more powerful X-rays.
Exactly.
Got it. Now, this is where I got a little confused. The source material talks about K-shell binding energy
Uh-huh.
and how it relates to the appearance of characteristic X-rays.
Okay.
And there's this point where these characteristic X-rays just suddenly appear on the spectrum. What causes that?
Right. That's a great observation.
Yeah.
So, the appearance of characteristic X-rays is directly related to the energy needed to overcome the binding energy of the K-shell electrons in the target atoms. It's like an energy barrier.
Okay.
If the incoming electrons don't have enough energy to overcome this barrier, they can't knock out a K-shell electron, and no characteristic X-rays are produced.
So the incoming electrons need enough energy to knock out the K-shell electron. They need a certain amount of, I don't know, oof, for lack of a better term,
Yeah, I like that. Oof. That's a good way to put it.
to get over that binding energy.
Yeah.
And what's interesting is that, according to the source, you can actually estimate this binding energy using the simulator. You can kind of become an X-ray detective.
Exactly. It's pretty cool. By adjusting the kVp and watching when those characteristic X-ray peaks first appear on the spectrum, you can figure out how much energy is needed to free those key shell electrons.
Oh, that's neat. So it's
Ah.
like a little science experiment. But I have a question about this binding energy. The source material mentions why the threshold energy, the point where characteristic X-rays appear, is higher than the actual energies of the characteristic X-rays themselves.
Right.
And I don't understand why shouldn't they be the same?
That's a great question.
Mm.
And it has to do with the fact that the incoming electron doesn't just knock out the K-shell electron, it also loses some of its own energy in the process.
Oh, okay.
So it's not just about the energy needed to remove the K-shell electron, it's also about the energy lost by the incoming electron during the collision itself.
So it's like if you bounce a ball, it doesn't come back up to the same height because some of its energy is lost as heat and sound.
Precisely.
So the incoming electron loses some of its energy during the collision, just like the ball.
Exactly. Great analogy.
Okay, I think I'm starting to get it. So we've talked about these two ways to create X-rays and how the kVp affects their energies and intensity.
Right.
But are there other things that can influence the X-ray spectrum?
Oh, absolutely. One of the key factors is filtration. And I don't mean the kind you use for your morning coffee.
Right.
This type of filtration is about shaping the X-ray beam. It's almost like fine-tuning the color of the X-rays.
Oh, interesting.
Yeah.
So it's not just about weakening the beam.
No, it's about changing its quality. See, different tissues in our bodies absorb X-rays differently.
Mm-hmm.
And by adjusting the filtration, technicians can optimize the X-ray beam to better penetrate certain areas while minimizing unnecessary exposure to others.
Okay, so it's a balancing act, basically.
Exactly.
You want to get a clear image, but you also want to keep the patient safe.
That's right.
So how does filtration actually work? The source material mentions something about a ripple factor. What is that?
Well, the ripple factor refers to variations in the voltage applied to the X-ray tube.
Okay.
So instead of a smooth, consistent voltage, there can be these tiny fluctuations. You could almost think of it as a little hiccup in the machine's rhythm. Yeah, kind of. And these hiccups can impact the X-ray output, primarily affecting the lower energy portion of the spectrum.
So is that similar to what filtration does?
You could say they both influence the spectrum, but in slightly different ways.
Oh, okay.
Filtration mainly removes lower energy X-rays, hardening the beam and making it more penetrating.
Okay.
But ripple, it broadens the energy range of the X-rays produced because of those voltage fluctuations.
So it's like filtration is a scalpel and ripple is a broad brushstroke.
That's a great analogy. Filtration is very selective, while ripple, well, it introduces a bit more unpredictability.
And I guess that's why you want to keep this ripple factor as low as possible, right?
You got it. Too much ripple can mess with the consistency of the X-ray beam, making it less effective for diagnosis.
Wow. So there are a lot of factors to consider when producing the right X-ray beam for each patient and purpose.
Absolutely. It's not just point and shoot. It's a delicate balance of science and precision to ensure the best outcome for the patient.
It really is a fascinating combination of physics and artistry.
I agree. And, we've only just scratched the surface. There's so much more to explore, like the specifics of how different filter materials work or the intricacies of how ripple affects image quality.
Yeah.
But hopefully we've given you a good foundation to build on.
Yeah, I think so too. This has been a really interesting look into the world of X-ray spectrums, and I'm sure our listeners have a lot to think about. Okay, so we've talked about how adjusting that voltage, the kVp, can change the energy and intensity of the X-ray beam, right?
Yeah.
And we've also talked about how filtration can really shape that beam so it's more suitable for imaging different tissues.
Exactly. And that shaping is really key. We're aiming for that balance, strong enough to penetrate, but not too strong to be a risk to the patient.
Yeah, that makes sense. So how does filtration actually work? I mean, the source material mentions a couple of things, like atomic number, density, and thickness of the filter material.
Right. So let's break those down a little. So first, we've got atomic number, represented by the letter Z, and that just refers to the number of protons in an atom's nucleus, right?
Mm-hmm.
And the higher the atomic number, the denser the electron cloud surrounding that atom. And that denser cloud, it's kind of like a roadblock for those X-rays.
Oh, okay. So a higher atomic number means the X-rays are more likely to interact with the filter material and get absorbed.
Exactly.
Gotcha. So then density, represented by the Greek letter rho, plays a similar role.
Yeah, think of it like trying to walk through a crowded room versus an empty one.
Okay.
You're more likely to bump into someone in the crowded room, right?
Yeah.
And similarly, the denser the filter material, the more likely those X-rays are to collide with atoms and get absorbed.
So that means higher atomic number and higher density both lead to more absorption.
Exactly.
Okay.
Yeah.
Then thickness, that seems pretty straightforward, right?
That thickness, represented by the letter D, just refers to how much of that filter material the X-rays have to go through, right?
Mm-hmm.
The thicker the filter, the longer the journey, and the more chances those X-rays have to get absorbed.
Gotcha. So all three, atomic number, density, and thickness, all work together to control how much of the X-ray beam gets through that filter.
Exactly.
But I'm still a little fuzzy on why this is so important. Why not just use a super strong beam every time?
Well, you have to consider the concept of differential absorption, right? Different tissues in our bodies, they absorb X-rays to different degrees.
Oh, right.
Like bone absorbs more X-rays than soft tissues, like muscle or fat.
Mm-hmm.
And that's what lets us see that contrast. In an X-ray image, the bones appear white because they absorb more, while the soft tissues are darker.
Okay. So if you used a beam that was too strong, you just end up with a totally white image.
Not exactly,
Yeah.
but you would risk overexposing the patient, which can be harmful. And a beam that's too weak, well, that won't penetrate the tissue enough, and you'll end up with a blurry image.
So filtration is all about finding that sweet spot, getting a clear picture while keeping the patient safe.
Precisely. By choosing the right filter material and thickness, they can tailor that beam to the specific area, ensuring the best possible results with the lowest possible risk.
That's amazing. I mean, it makes you realize how much goes into taking an X-ray. It's not just a simple picture.
It really is a testament to those who developed this technology, taking these physics principles and creating this tool for diagnosis and treatment.
It really is a blend of science and artistry.
I like that. I like that. And we've covered a lot today, from the different ways X-rays are produced to these factors that shape their energy and intensity.
Yeah.
But is there anything else about X-ray spectrums our listeners should keep in mind?
Yeah. Is there?
Well, it's important to remember that the X-ray spectrum isn't static, right? It can be influenced by a bunch of things like the type of X-ray tube, how old it is, and even things like temperature and humidity.
Oh, wow. So even with all these controls, there's still some variability.
Exactly. And that's why it's crucial for technicians to be aware of these factors, to calibrate their equipment regularly and ensure those results are consistent.
Yeah, it shows how important expertise and training are in this field.
Absolutely.
Now, earlier we talked about how different tissues absorb X-rays differently and how that lets us see that contrast in the image. Can you expand on that a bit more?
Sure. So how much a tissue absorbs X-rays is related to its density and atomic number, right? Denser tissues like bone with higher atomic numbers, they absorb more X-rays, and that's why they look white or lighter on an X-ray image.
Right.
But softer tissues like muscle or fat, they have lower densities and atomic numbers, so they absorb fewer X-rays and appear darker.
So it's that difference in absorption that creates the contrast, letting us see all those different structures.
Exactly, and that's, fundamental to X-ray imaging. It lets us see bones, organs, even some soft tissue abnormalities without, needing more invasive procedures.
That's incredible. It's like physics revealing the secrets of our bodies.
It really is. But before we wrap up, I have one last thought.
Oh, okay.
We've discussed how different tissues absorb X-rays differently. But what about the target material itself? The material those electrons hit to produce those X-rays.
Right.
Does its composition influence the X-ray spectrum?
That's a great question.
It is, and it's something we could dive into another time. The target material does play a role, but I think we've covered a lot already today.
Yeah, I think we've given our listeners a lot to think about for sure. This has been such a fascinating look into the world of X-rays, and I hope everyone listening has a better appreciation for the science and tech behind this important medical tool. So we talked about how that target material can actually have an impact on the X-ray spectrum.
Yeah.
But before we finish up, I want to go back to something you mentioned earlier about the ripple factor.
Okay.
You mentioned it affects the lower energy part of the spectrum.
Right.
Can you walk me through how that works?
Sure. So remember, the ripple factor is all about those fluctuations in the voltage.
Yeah.
Go to that X-ray tube.
Uh-huh.
And these fluctuations, they mean that the electrons hitting the target, well, they don't all have the same energy.
Oh,
Some have a bit more, and some have a bit less.
So that would lead to a wider range of X-ray energies.
Exactly. It's kind of like, imagine a choir where not everyone's singing exactly the same note.
Oh, yeah.
You can still hear the melody, but it's not quite as clear.
So a higher ripple factor means a less precise X-ray beam.
You could say that it adds a bit of uncertainty, which can affect how clear the image is,
Yeah.
especially for those, really detailed images.
Makes sense. So minimizing that ripple factor is important for getting the best image possible.
Absolutely. Modern X-ray equipment, it's designed to keep that ripple factor super low, but, it's still something technicians need to watch.
It's pretty amazing to think about all the things that go into getting a good X-ray image.
Yeah, it is.
It's not just point and shoot, it's really precise.
Yeah, it's a testament to, all the physicists and engineers behind the scenes making this tech work.
Well, I think we've given our listeners a lot to think about today,
I think so too.
We started with those fundamental physics of X-ray production. Then we talked about the stuff that shapes that X-ray spectrum and the role of filtration.
Filtration's so important.
Yeah, that balance between a clear image and keeping the patient safe.
Exactly. It's all connected.
Hopefully everyone listening now has a deeper understanding of this tech and, the science behind it.
And maybe even inspired someone to, explore a bit more about X-ray science.
I hope so. There's always something new to discover, right?
Always.
Well, on that note, we'll wrap up this deep dive. Thanks for listening, everyone, and keep those questions coming.